Streaming. Okay. Hello, if anybody happens to be here. Usually people take a second to show up, so let's go check YouTube, make sure the streaming is going as expected. Your channel, week 9. This is not week 9. Manage videos. Let's see. Live. We'll say right here, we'll edit the title. This is week 12, and this week we will be discussing, what is this? Object-oriented design patterns. Oh, Rajat! Hi! How are you? Good to see you. Object-oriented design patterns and software and design philosophy. So work has calmed down. Hi, Josh. Had a phone call today. Looking good. Looking good. I expect you expect you're going to have somebody reaching out to you soon. That seemed pretty positive overall. I imagine that an offer is in the works. Wait. Oh, Stream Elements bot running. Did that show up in my... No. Yeah, no, it was a full half-hour conversation, and yeah, I obviously we're streaming live, so I don't actually want to go into personal details or anything, but yeah, seemed to go okay, and yeah, that's the story. Let's see what else. So I went through on this week's sort of like looking around for materials and things, and the object-oriented design interview questions. Yeah, I'm really excited to know what happens. I think you're in good shape though. Oh shoot! You know what else I haven't done is I haven't paired my headphones with the TV. So if we are going to be watching videos, I've got to deal with that too. Anyways, so yeah, so I went through the object-oriented design videos that were online that I could find, and there weren't any that were super engaging and had that right level of like audio quality and video quality to like rebroadcast them. So I'm leaving those out, but I did find some written materials. So just like is discussed in the coding interview roadmap document, they link to this. There are a couple of so there's the full course. You can always buy the full course, but they have a couple of samples in here. The samples include design a parking lot and design a library management system. And these are long. They're long, and they look super complicated, especially around this stuff. Like, this is UML. Hello, UML. And these sorts of flowcharts and things are really interesting because all of these little stars and numbers and triangles and white arrows and black arrows and all of that stuff has, yeah, UML, the flowcharts. So you've already seen this stuff. So each one of these things that you're seeing, the dotted lines, the straight lines, they have semantic meaning. And so, and then stuff like, I mean, this one doesn't have it. So it's important at a high level to sort of have a sense for what UML is and how it works. I would not expect that you would be asked in an interview situation to answer UML type stuff. I imagine there are places in the world, classes with data stored methods for retrieval and lines indicating uses and interrelationships. Yes. So the lines and things, but so the and I actually have video references for talking for that will sort of go through the basics of UML, and we can deal with that in a bit. But something, for example, when we're talking about inheritance, a book is this looks like it's probably well, so a book is an abstract class because book is this appears to be in italics here, right? And so abstract classes are in italics, and so a book item, I suppose, inherits from a book, and that's what this type of arrow means, that it has. So a book item would have all of these fields, but it would also have all of these fields, and you can see that by looking at the diagram if you know how to read the diagram, because this unfilled arrow means that it is an inheritor, that or so it's a book item is a book, and then so a librarian and a member, they both have they are both accounts, and so the accounts have these fields, but also the librarian, for example, has these ones. And so that's how this stuff sort of works, and I've got a video on how to understand the yeah, and like Rajat's saying, it's the arrows have meaning. The like for example, this 0.5 would mean that an account can borrow anywhere from 0 books to 5 books. So they have a limit. They can reserve anywhere from 0 books to 5 books. An account can have at maximum an account can have at maximum 1 library card. This sort of double-filled diamond means that the library card cannot exist without the account, but the account can exist without the library card. Or maybe that's the other way around. I don't know. I mean, I'm just figuring this stuff out too. But as part of like the starter introduction to object-oriented design questions, I wanted to draw attention to these 2 pretty good write-ups. And I would suggest that if you are coming to a position where you expect to have object-oriented design questions, that these would be the places where you would want to start your refresher. So again, you look here we are. We have all of these things, and all of these things have semantic meaning. But again, we're going to go through it, and but so since we've already done a number. Wait, I love how engineers know how to lay out data in a way that other engineers who have never seen that structure. Yeah, right. I mean, that's part of what UML was designed to do, and knowing what these triangles and arrows specifically mean just takes your ability to read this to the next level. And so I think that's probably what I want to start with on the topic of object-oriented design. So this is sort of like prepare and brief for the expectations of the interview. So the types of questions that you would get are exactly that. It's like design a parking lot, design an elevator system, design an ATM, and these are like evidence documents that show you what a complete correct answer would look like. Again, but I think the interesting part for foundational, here's the 10 minutes on UML. Give me a second to pair my TV so that I can make sure that our sound is good. I'll pop this in. Otherwise, we're gonna get like crazy echo when I do this. Select speaker, Bluetooth audio, AirPods Pro, connect. AirPods connected. Okay, so now, oh, one more second. Here we go. So this guy is going to tell us about UML class.
Hi, my name is Zach and I'm with Lucidchart. Today I'll be teaching you about UML class diagrams. We'll start with some of the basic characteristics, then we'll talk about relationships, and we'll finish up by going through some examples together. Alright, let's talk about some of the basic characteristics of class diagrams. To help explain these characteristics, I'm going to make up an example to help illustrate. So let's say we're building a system for a zoo. And, by the way, these examples I'm going to use probably would never find their way into an actual program, but it'll make all these concepts easier to understand. So in our zoo, we'd want to describe the different things that are in the system. You represent those things through classes, and a class is depicted with this shape here. So what's in a zoo? Well, there are a ton of animals, so we could create a class for our animals. To do that, you just write the name of the class in this top section. If our class is animal, an instance of that class would be a specific animal. So the question is, how would you go about identifying each instance of that class? You do that through attributes. An attribute is a significant piece of data containing values that describe each instance of that class. They're also known as fields, variables, or properties, and they go in the middle section here. So for our animal class, we could create attributes like name, ID, and age. That way we could identify a specific instance of the animal class, like Ruth, ID number 304, age 114. These need to be formatted a certain way though. You start with visibility, which we'll talk about later, the name of the attribute beginning with a lowercase letter, then you follow it with a colon and the data type. For the name, we'd want to return a string, and we can format the other attributes the same way, except that we'd want to return an integer since these are numbers. Now that we've got some attributes for our animal class, we get to the bottom section here. This is where you put methods, which are also known as operations or functions. Methods allow you to specify any behavioral features of a class. So we might ask ourselves, what are some different behaviors of this animal class? Maybe we'd want to be able to change our animals' names. Like Ruth should actually be called Rita. So let's create a function called setName. We could also create a method for eating since all of our animals eat. Methods also need to be formatted a certain way. You start with visibility, which we'll talk about next, then the method beginning with a lowercase letter.
Next, you put parentheses to signify the function you're going to program later. You can also add variables and the data type in here, but in most cases, it's not really necessary. We'll add visibility and parentheses to the eat method as well.
Now let's talk about the visibility. The visibility of an attribute or a method sets the accessibility for that attribute or method. So right now we have a minus sign for all of these, which indicates that each of these attributes and methods are private. They can't be accessed by any other class or subclass. The exact opposite is the plus sign, which means an attribute or method is public and can be accessed by any other class. Another visibility type is indicated by the hash, which means an attribute or method is protected. These can only be accessed by the same class or its subclasses. And finally, there's the tilde, or the squiggly as I like to call it. This sets the visibility to package or default, which means it can be used by any other class as long as it's in the same package. But that one is rarely ever used. In most cases, your attributes are going to be private or protected, and methods are often public. Let's quickly review these basics with another example.
Here we go. So that's pretty straightforward. And now, I think for learning UML, we've got our two examples here. And so you can kind of, I wonder if I zoom in on this, well, it's not really, here, open image in new tab. I should have done better at preparing that. So anyway, so what you see, now these UML diagrams don't actually have the minus or plus. And I don't know what that means. I know that in the video that he's showing, he says, at some point he says, all of my properties are going to be private, so we'll just leave it out and assume that. But I don't know what that means in this context. But right away, you know that everything up here in your UML diagram is a variable that lives on the object, and everything underneath the line is a function or a method. So this one has no method, this one has, and so that's the first part of learning how to read UML, is just understanding the convention there. And so we'll keep going back to this and sort of bounce back and forth after every major concept to like connect to real world UML diagrams. So I'll move it to this one as well. So you say, like you look again at this one. Can I minimize this? No. You look again at this one and you see you've got your book with all of these are the fields. This is a function called get title. Here's a function for checking out the book. That's part one of UML class diagrams.
Let's make a class for employee. We could give an employee the attributes of name, employee ID, phone number, and department. We'll want all of these attributes to be private, and then we could create a simple method like updating the phone number, which we'll go ahead and set to public. So you may have noticed that I'm using diagramming software to create these UML class diagrams. The same principles apply if you're using pen and paper, but diagramming software makes it much easier. The diagramming software I'm using today is Lucidchart, and you can sign up for free by clicking on the link at the top right. All it takes is an email address, and then you'll be able to follow along as we make these class diagrams. So the next thing we'll need to cover are the different relationships that exist between classes. The first type of relationship that we'll describe is inheritance. I'm going to keep going with the zoo example because it makes it easy to understand the logic of these relationships. We'll get to a more technical real-world example later. Okay, so inheritance. Let's say in our zoo, the only animals we have are tortoises, otters, and the lesser known, but none the less amazing slow loris. In our system, we want to distinguish each of them as their own class. So we make 3 new classes for tortoise, otter, and slow loris.
And I'll make these a little smaller so you can see them better.
Now, instead of duplicating attributes for name, ID, and age, we can make these classes into subclasses of the animal class by drawing open arrows like this. This is an inheritance relationship. We're saying that these subclasses inherit all the attributes and methods of the superclass. You could also use the terms child and parent class. So our otter class is going to inherit the attributes of name, age, and ID. And then we could add an attribute specific to otter like whisker length. One of the advantages of inheritance is that if we wanted to change or add an attribute for all animals, we wouldn't have to go in and make that change to tortoise, and then otter, and then slow loris. We could just make the change to the animal class and it applies across all subclasses. In this scenario, we also have what's called abstraction. Animal is an abstract class. Because in our system, anytime we want to instantiate one of our classes, it's going to be a tortoise, otter, or slow loris. We wouldn't instantiate the animal class itself. The animal class is just a way to simplify things and keep the code dry so you don't repeat yourself. So to show that this is an abstract class, we'll put the name in italics. You could put the name inside these things as well, but I prefer italics. Okay, another type of relationship is association. So if we had a class for sea urchin, we could draw an association, which is just depicted by a simple line, between otter and sea urchin. And we'd say otter eats sea urchin. There's no dependency between them, it's just a basic association relationship, and it's pretty simple. The next type of relationship is aggregation. It's a special type of association that specifies a whole and its parts. So to continue with our zoo example, again, this is just to help explain the logic, let's create a new class for a group of tortoises. A group of tortoises is called a creep, and that's pretty cool. So here's our creep class, and it's got a relationship with tortoise. Any of our zoo's tortoises could be part of a creep, but they don't have to be. A tortoise could leave the creep at any point and still exist on its own. That type of relationship where a part can exist outside the whole is aggregation, and we note it with an open diamond. There's also a relationship where the part can't exist outside the whole. It's called composition. To illustrate this, I'm going to create a few new classes. Let's just say we have several different visitor centers in our zoo, and each of those visitor centers has a lobby and a bathroom. Now, if one of our visitor centers was torn down, the lobby and the bathroom of that visitor center would be destroyed as well. Those rooms couldn't exist apart from the visitor center that they're in. That's composition, when a child object wouldn't be able to exist without its parent object. We note a composition relationship with a closed diamond. Another important concept when talking about relationships in UML class diagrams is multiplicity. Multiplicity allows you to set numeric.
Here we go. So that's a good spot. Hi, Glenn. Thank you for coming. So, Glenn, to catch you up, we're sort of going through the object-oriented, just sort of object-oriented concepts and talking about sort of the important high-level theoretical concepts to wrap your head around, because in going through all of the available object-oriented design interview questions that I could find. They were all super boring and not very high quality, so I thought I would find stuff that was higher quality. And to catch you up again, we're learning about a process used, or a set of tools that are used within object-oriented design called UML. UML, or I don't know, it's probably like universal markup language or something, which somebody can maybe Google for us while I'm moving around. Let me Google that and find out what UML stands for. UML stands for Unified Modeling Language. So like nothing like what I said. Anyways, so what we were just talking about was each of these types of arrow endpoints has a semantic meaning. And if we go back to the unified modeling language, so the, where was that bit right here? Here we go. So we have inheritance, association, aggregation, and there was, here's one, aggregation, and just show me the dot.
The part can't.
Doesn't matter. So a open arrow point means inheritance. An association means that they're related, but not really, but they can exist separately and they're not tied to each other. Composition was the last one. Aggregation, do these diagrams have any aggregations? No, these are, so these diagrams, does this diagram have an aggregation? It also does not. But so we're talking about how in order to sort of wrap your head around how the inheritance hierarchy works or how the class diagrams work, it's like everything in this top box is the names of the variables that are attached to the object. Aggregation was the tortoise example in the video. Yeah, so an aggregation is a tortoise can be a part of a creep, but the creep can exist without the tortoise, and the tortoise can go in and out of it. Anyways, so we'll keep going. I jumped back a bit. Let's jump forward to here where we are doing the multiplicity.
Let's say we want to specify that our visitor centers are going to have just one lobby. We simply write the number 1 here, meaning that there can be one and only one lobby per visitor center. But for bathrooms, maybe we want to make it so that there's at least one bathroom per visitor center, but leave the option to have as many as you like. We'd use this notation to denote one or many bathrooms. Other types of multiplicity are 0 to 1, which is an optional relationship, n representing a specific amount, which in our example was 1, but it could be any other number depending on your use case, 0 to many, 1 to many, or a specific number range. Hopefully our zoo examples have helped explain those concepts, but I want to show you what a real-world example would look like. This is a UML class diagram for an online shopping cart, and if you want to look at this diagram with me, just click the link in the top right corner. You can see that the system has several classes and relationships, so let's walk through a couple of them. We'll start with the user class. It's got attributes for user ID, password, login status, and register date. You've got the different return types on the right, and on the left.
Oh, sorry. Here we go. Here we go. So we can look at this. You can see the customer order, shipping info. So a customer has one shopping cart, or 0 to many shopping carts. Customer exists with or without a shopping cart. There's many to n, any number. Shouldn't 0 to many, or yeah, I don't understand. Why are we saying a shopping cart can have, this one's easy to understand. So it's a shopping cart can have at least one, can have at most one and exactly one customer, and a shopping cart doesn't exist without a customer. Is that what that says? Yeah, it's one customer, 0 to many shopping carts. So one customer can have multiple shopping carts. I haven't seen that ever, but I mean, it makes a lot of sense that you could have buying for now, buying for later, whatever. So there you go. And then you can have an order can have one customer. You can't have an order without a customer. A customer can have 0 orders, but they could have many orders. And it's just, how do you read the object design of the entire system in a somewhat more visual way, because you're looking at how these things are related to each other, and that's a lot easier to wrap your head around than just a long list of file names, and you think, well, how do these things tie together? So these UML diagrams are super, super valuable, but learning how to read what does this type of triangle mean, or what does this type of filled in diamond mean, is also really valuable in terms of long-term understanding of how all of this stuff works.
Left, visibility, which are set to private. You can see how the values returned by these attributes would specifically describe an instance of the user class. Down below, we have a public method of verify login, returning a Boolean. And this makes sense, right? Methods are behaviors of a class. So if you were to log into your user account, there's a function in place that verifies your login credentials. Let's move on to the customer class. This arrow tells us that customer is a child of user. So customer inherits all of the attributes and methods of the user class. And same thing for the administrator class. Both of these inherit from user, but also have their own specific attributes and methods. Like administrator can update catalog, but customer can't. Stemming from customer, there are several lines with the closed-in diamond. So if you recall, these are composition relationships, which means that the parts cannot exist without the whole. If an instance of the customer class, if that customer's account was destroyed, his shopping cart would be destroyed and his orders would be lost. They can't exist outside of the customer. The same applies for shipping info and order details. If there's no order, there's not going to be any order details or shipping info. The last thing we'll look at in this example is multiplicity. You can see that a customer can have 0 or many orders. Makes sense, right? You could create a customer account for an online store but never buy anything. Or you could be a frequent customer and place several different orders. And on the flip side, an order can belong to only one customer. It'd be pretty confusing if a specific order with a unique order ID was duplicated across several different customers. And here you can see a one-to-one relationship. Each order has one and only one order details, and order details belongs to one and only one order.
Thanks for watching this tutorial on UML class diagrams. Be sure to subscribe to the channel and leave a comment below. Lastly, don't forget to sign up for a free Lucidchart account by using this link, and you'll be able to start making your own UML class diagrams in no time.
So that's the sort of UML side of things, and I only really I knew the flowcharts all probably had meaning, but when you really dig into it, it's really helpful and useful to know. And hi, Pabs, thanks for showing up. What else do we have? So that was the start of that. And what else? I really liked this guy, and I'm trying to decide if we go to him. No, let's go to the design patterns, source making. So the design patterns themselves are we'll start with the video from Smock, and he gives an overview of what design patterns are in particular, and why they are valuable within the scope of object-oriented design. And then we'll look at some of the resources around design patterns, and then delve a little deeper as well.
Hello and welcome to Smock Dev Workshop. This is an introduction to design patterns. We'll start with the basics. What are design patterns and how they came to be? What design patterns are not? why use them, and when is a good time to learn them. Then we'll go over what design patterns are there, and I will try to point you towards some further reading. But before that, I'll just mention that my name is Rafał, and I am currently working for Amazon Prime Video. And this series is not meant as a definite reference for this topic. It is supposed to help you start exploring and researching design patterns as you come to need them. When I first heard about design patterns, they seemed mystical, extremely hard topics that were used to scare junior developers. As you'll see in a second, they are not as scary. But what are design patterns? Webpage javadesignpatterns.com, which I deeply recommend, says design patterns are the best formalized practices a programmer can use to solve common problems when designing an application or a system. Nice! So we can avoid some common pitfalls by following something that is prepared for us by devs with more practice. Such design pattern consists of 4 things. 1. A good, clear name that is short and accurate abbreviation of the design pattern. 2. A description which explains the solved problem in depth. 3. An actual solution described in a possibly abstract way. 4. Consequences of using the pattern, both good and bad. That is still a bit vague, so let's throw in a little story. The first book on design patterns was written by 4 computer scientists: Eric Gamma, Richard Helm, Ralph Johnson, and John Vlissides, also known as Gang of 4, or GOF in short. Over the years of their experience, they reviewed the code in systems they were working on and extracted the most common best practices, which help different developers across organizations to reach good results. They came up with a little over 20 patterns and described them in a book like this one. Well, obviously, this is a Polish version, but you can get English one online. The most simple example of design pattern I can think of is a singleton, which in plain words ensures that only one object of...
You notice the UML on the on the single malt scotch? You know that now.
Singleton, which in plain words ensures that only one object of particular class is ever created, and singleton will provide a global access to it. Got it? Nice! What design patterns are not? Design patterns are not algorithms. They are meant to provide a guidance on structure, relations, and hierarchy of objects, classes, and interfaces in the application, and they are a way of thinking about abstraction, not so much about underlying data. They don't solve every problem. Sometimes situation may require from you to choose one pattern over the other, and you may get it wrong. But don't worry. The upside is, even making such a mistake is oftentimes better than coming up with a different solution on your own. Because most likely you saved yourself a lot of trouble that may come from different places you haven't thought of. But remember, don't use them if they will make your code more complex. They are meant to simplify things for you,
not the other way around.
So make sure you understand the pattern well, do practice it in isolation before using it in production code. Alright, so why use them? Reusing design patterns will help prevent subtle issues which may cause major problems. They are agreed terms improving code readability for coders and architects who are familiar with these patterns. In other words, if you know the pattern, you can quickly recognize it in the code and get the gist of it without reading every line. And the other way around. In office communication, it is simpler and more precise to discuss possible solutions using patterns that your team knows and understands. rather than describing the solution piece by piece every time you get back to it. And like algorithms, they are universal to every object-oriented language. So learn once, benefit forever. Aspiring developers ask, when is it a good time to learn design patterns? My answer is, don't rush it. First, get around knowing and practicing basic programming principles like KISS, DRY, YAGNI, and so on. Learn data structures and algorithms. Get to understand object-oriented programming. And by that, I mean fundamentals of this paradigm. Encapsulation, abstraction, polymorphism, inheritance, and composition. Make sure you understand differences between interface and base class, abstract versus concrete. Also, I want to clearly state that you don't need to learn every single pattern there is, or learn them in any particular order. You obviously want to start with the most common to understand what other people are talking about. But after that, you're free to explore what interests you. And as I said previously, start shallow and broad. Skim through as many as you can at the beginning. When you know what they do, go deeper, only if you need to. So,
I mean, I thought this guy's introduction was really, really nice and concise, and he makes a strong case for why you want to get an understanding of the design patterns. And so that's what we're going to try and go through. It establishes a common language across you and your coworkers. And so, one of the, as we saw, there's that one design pattern called a singleton. And so that's a single word that describes an entire concept for a huge chunk of things that are going on. And so knowing the names of the design pattern and generally what they represent, that will give you a leg up when you are trying to communicate with other programmers on your teams about how you are going to write the software that you're about to write together. And so there's the value in that. Pabs, I assume that have you done a full course on design patterns? Because you have your CS degree, don't you? Because I don't, and so I'm like getting up. I mean, you kind of come across. 10 years, 20 years in the business. Of course, I've worked with singletons before, but diving in and really digging into what does singleton actually mean on the lowest level is really valuable in terms of being able to work on broader teams. So let's keep going.
what design patterns are there? Gang of Four proposes 3 categories: creational, structural, and behavioral. Other sources also suggest functional, concurrency, architectural, cloud distributed, and others. Let's start from the most commonly known Gang of Four design patterns. The creational design patterns are obviously responsible for efficient object creation mechanisms, which will increase the flexibility and the reuse of existing code. Under this category we have factory method, abstract factory, prototype, builder, and singleton. Structural design patterns are responsible for building simple and efficient class hierarchies and relations between different classes. They consist of adapter, bridge, composite, decorator, proxy, facade, and flyweight.
I've heard that head first design patterns is actually funny and has jokes in it and is easy to read. So I also have Gang of Four, but I have since learned that head first is a much more approachable version of the same one. So it's apparently filled with jokes and things. That's the one.
Behavioral patterns define manners of communication between classes and objects. This is the longest list: template method, chain of responsibility, command, iterator, mediator, memento, observer, strategy, state, visitor. In following videos, I'll go deeper into those, so you can understand how they look, how they work, how they feel like, what are they about. So do stick around, and if you rather grab a book, read more online, look into description for some good references and suggestions. And that's it for today. Subscribe, comment and share. Cheers!
First of all, that was such a good, like, when you go through this tech stuff at length, you go through a lot of programming guides online. So much of it is really dense and really hard to process. They might have bad sound quality, but I thought this guy was really, really good, especially that intro just sort of summarizes everything really good. It would be interesting to see if there are design patterns for front-end stuff. It's funny, right? Because that kind of stuff seems to be emerging in, React versus Angular, and we've gone even just the two-way data binding versus one-way data binding, like that kind of stuff really is emerging in the front-end space, but maybe we need a few more years and then componentization versus other stuff. So maybe we just need somebody to write it all down. So in Smock's design patterns introduction, he mentioned there are three major design patterns, or three major clusters of design patterns. And you'll see this book here, sourcemaking.com, design_patterns, that is linked in the guide right here, has a pretty good text summary if you would like to read them. So you can go in, you can find out what is an abstract factory, how is it intended to be used. So this is a large, it's pretty good. Support our free website and own the ebook. So it's like these guys have a lot of content. There are creational patterns, structural, and then in terms of what your options are for going deeper on been only using functions now in React, functional program. Yeah, and functional programming really is, I'm hearing more about it, and it seems to be taking hold in a lot of people are way more interested in the functional programming space right now. Or maybe they always have been, and I'm just noticing it more, but yeah. So anyways, so I wanted to go through and talk there were actually three major, one of them I did not save, it looks like. There were three major really good content creators on the design patterns space. Smock is one of them. The other one is Christopher Okravi. And so Chris has gone through and created a playlist where he goes through virtually the entire Gang of Four book and breaks it down one video at a time. And I thought this guy was pretty good, but also it's like a million years, and we're not doing like an hour and 40 minutes on the iterator pattern. We don't have to do that here and now, but his stuff, we can watch a few minutes of this just for a second.
Welcome back to another video on a design pattern. In this video, we are going to...
That's enough. That's enough. So he has pretty good production value. So if you want to learn design patterns in detail from him, that's a good place to go. Honestly, makes more sense on front end when I look at the object orient. Yeah, I think you're right. I mean, object oriented on the front end is, I mean, it has a bit of a place, but like, everything's so event driven. Yeah, I think so. And like Pebs is saying, how it does swing back and forth. So on to Smock again. Well, let's see, 746. I actually really like this. I think I want to go through this one for a bit, and if there's time at the end, we can go back to the specific design patterns. I want to make sure that you have the resources available to use them if you want. But this guy doing the philosophy of software design. John Austerout, he created a Stanford course where they, I guess he sort of started, there's the concept of the 10x. I'm starting the philosophy of software. Oh, you're actually reading this one right now? Because I was just about to read it as well. I just got a copy. So yeah. Oh, so for his intro, it's all just housekeeping stuff, and it's not super relevant. This is about where it starts, and then he talks. He has interruptive questions, and so for some of them, if I catch it in time, I'm gonna skip some of them. But this is, I think, a very good presentation. So
okay, so people have been programming computers for more than 80 years now, and yet software design is still basically a black art. There's essentially no agreement on how to do software design or even what a good piece of software looks like. We talk a lot about software engineering and software tools and testing and processes, but we have almost no conversation about the fundamental act of designing software. And this has bugged me for a long time. So today, I'd like to tell you about some things I've been doing to try and change that, to start the conversation, and to see if we can somehow create a greater sense of design awareness in the software community. And that consists of a new course I developed at Stanford, and then based on that, a book on software design. OK, so let's start with the basics. If you had to pick one idea, one concept that's the most important thing in all of computer science, one thing that threads through every aspect of computer science, from AI to systems to theory, first of all, what would you pick? Abstraction? Sorry? Testing. Other ideas? Sorry? Composition? Sorry? Complexity? So I asked Don Knuth this question. He said layers of abstraction, which I would say is almost right, although some would say by definition it's right. What I would say is problem decomposition. How do you take a complicated problem or system and chop it up into pieces that you can build relatively independently? And yet, as far as I know, aside from what you're going to hear today, there is no course anywhere where that concept is one of the most important ideas in the course. We simply don't teach it. Second, we all know that some programmers are way, way more productive than others. Google has coined the term the 10x programmer. And yet, as far as I know, no one attempts to teach these skills either. And these ideas have been sitting in the back of my head and bugging me for a long time. How can we have these things that are so important, and yet we don't really make any attempt to teach people this stuff? If you're a great programmer, somehow you just figure it out on your own. So that leads to the question, can we do this? And there's three questions there. First, is it even possible? Is this just a sort of innate skill that you're born with in your genes, or is it something that can be taught? So first, let's do a quick survey. How many of you think this is something that's, either you have it or you don't, you can't really teach it, it's just sort of an innate skill? A few. How many think that this could be taught in some way or another? Good. A few summers ago, I read a really great book by Jeff Colvin titled Talent is Overrated. If you want a fun read, read it. It's a relatively quick read in which he goes through study after study that shows in these fields where we think of some people as being tremendously talented. In fact, the only thing that really differentiates the top performers from the average performers is how much they practiced. That's the one consistent correlating factor they can find. It's all about practice. So that got me thinking, I believe it's got to be possible to teach this. But the second thing is, who's going to do it? Well, unfortunately, not most of today's faculty. Problem is, typical faculty member writes a little bit of code as a grad student, never really gets any instruction. You throw out some crappy code for your dissertation, and then you become a professor, and then you decide coding is what graduate students do, so you stop coding, and you never write any more code. And so, the only way to become a great developer and learn design skills today is with tons of personal experience or trial and error. Faculty don't have that, so they can't teach their students, and so the whole process just continues over and over and over again. But fortunately, I'm not one of those faculty members, so maybe I have a better chance of doing this. So personally, I love programming. Programming is really one of the top 2 or 3 things I live for. My family, programming, really bad golf game. There's sort of a few things like the things that drive my life. But if I don't write 5,000 lines of code a year at least, I feel like it hasn't been a great year for me. So over my career, I've probably written, I think now, 250 to 300,000 lines of code. So I've had a chance to observe a lot. And again, as I've been doing it, I've been thinking about design stuff. So I thought maybe if anybody can do it in academia, I probably got about as good a shot as anybody. Then the third question is, well, how do you do it? So I combined all these three things together. I finally decided only one way to find out. I'm just going to have to try it. Maybe I'll crash and burn, but I'll give it a try. So I created a new course at Stanford, CS 190 Software Design Studio. It's not taught like a typical programming course. It's taught more like the way you learned English writing in high school with an iterative approach. So and the way you learn writing is you write something, your teacher marks it up, you get it back again, you rewrite, they mark it up again, and so on. And the whole process iterates several times. And it's that process of getting criticism, incorporating the criticism, and learning and seeing how that makes things better. That's how you become a good writer. So I thought we'll try the same idea in the class. And so that's the way it works. Now, we only have 10 weeks in a quarter system, so we can only do 3 iterations of this cycle. But the basic way it works is, in the first couple of weeks of the course, students in teams of 2 build the largest system they can possibly build in 3 weeks. That's typically about 2,000 to 3,000 lines of code, so still not a huge system. Then, after week 3, we go into code review phase. Students read each code and write reviews, and I read every single line of code written by all of the students. This is sort of one of the limitations of the class right now. So I end up reading 20 to 30,000 lines of code in that week. And then we do code reviews in class, where students will present pieces of their project and other students will critique it. And then I do longer code reviews. I read everybody's projects. I typically make 50 to 100 comments on every team, and then I meet with the teams individually for an hour and go over it with them. Then the second phase is they revise based on the code reviews. They actually add a little bit of additional functionality as well in the second phase. We do another round of code reviews, and then the third phase, they get a new project. They start from scratch. Again, and we finally do a third round of code reviews. And when they do this, the students get no ideas from me about how to design. I just tell them what the system has to do. They have to start from scratch and figure everything out themselves. So they make lots of mistakes in the first phase, but that's part of the learning of the class. Yeah, no question. Mike's coming in.
Watch a YouTube video on the same topic you gave, and in that one, phase 3, it was pass the project to the person on the left and inherit someone else's code. Why did you change it?
Yeah, the first 2 times I taught the class, I actually scrambled the projects in the third phase and made people add onto somebody else's project. That was a good learning experience, but the problem is people end up spending a lot of time decoding other people's projects and being frustrated with it. That has some value, but they didn't spend as much time doing real design stuff. And so I finally decided if what I really want is to teach people design, I think they'll learn more if they get to start from scratch and do a new design project. So I changed it. I may change back again. I'll try this for a while. OK, so that's the basic idea of the course. Now you may be wondering, but so what are the magic secrets? How do you do software design? And by the way, what makes me think I know what the secrets are? So first of all, I don't claim to know all the answers. I have some ideas that have kind of coalesced in my mind over the years, which I'm using in the course in the book.
Here, he skips off of this one, so it... Yeah, not only that, but like for the entire course, every student, every line of code. But he skips off of this frame pretty quickly, so I wanted to leave it up so you have enough time to read it. In fact, if I hit print screen, I can do this, capture the image. I'll pull that off. We'll keep playing.
Those are the end. Actually, I'm hoping more to use those to start a discussion and evolve them over time. But in the class, there's about 10 high-level ideas. They're very abstract, almost philosophical. I can't give you a recipe. Follow these 10 steps and you will produce a great design. I'm not sure that there is such a recipe. So instead of these vague ideas that I talk about while students are doing their first round of design, I'm not sure they sink in very well because they're so abstract. It's sort of probably hard to figure out how to apply them. The way
that
they
side
work
better?
best, though, is when we do the
Sorry.
codings. Then I can show the students how they violated some of these principles and what the consequence was in their code and how they should change it. And then they can go back and apply the principles as they revise. And then I think the ideas start sinking in. So it's sort of a question and back.
I'm curious what you think about how does the sort of end-to-end principle in sort of software design factor into this in terms of trying to push all the complexity to the edges of the system.
End-to-end
So
principle.
like the typical example of TCP, the checksum is at the is done end-to-end. It's not in the intermediate router stages, and that was a design principle that they had.
I'll have to think about that. I'm not sure that relates in a direct way to these principles, but I'll have to think about that. So there are these vague principles. Then the other thing I try and do is talk about red flags. So red flags are very specific things that if you see this sort of behavior or pattern, you're probably in trouble. And actually, I think for beginners in particular, red flags are really useful to people. Because even if you don't know how to design the right system, if you can see you're going wrong, then just try something else until eventually the red flags go away, and you'll probably end up in a pretty decent place. So red flags are really very useful. So what I'd like to do is I'm going to talk about the 4 things that are in red, just to give you a sense of some of the ideas. 2 of them are design principles. Classes should be deep, define errors out of existence. And 2 of them are more about mindset. I'll talk about those. So the first one is this notion that classes should be deep. This is really just another way of thinking about this idea that the idea of information hiding that David Parnas first put out in a paper in the early 1970s. By the way, to me, this paper is one of the 2 most important classic papers in all of software design and engineering. Has anybody here read this paper, classes? Great. It's still topical and relevant today. The last third, maybe not so much so, but the first part still, and it's got a great example and easy to read. So the way I think about a class as a rectangle. And the area of the rectangle is the functionality that class provides. So you can think of that's the benefit that the class provides to the rest of the system. Then think about the top edge as that's the interface to the class. And by interface, I mean everything someone has to have in their mind in order to use that class. It's not just the signatures for the functions, but things like side effects and dependencies and things like that. That's really the cost. You think of that's the complexity cost that this class imposes on the rest of the system. So we'd like that to be as small as possible. So ideally, what you'd like is the greatest benefit, least cost. So you'd like the smallest interface and then the largest area. So the opposite of that I call a shallow class. So that's something that has either not a whole lot of functionality or a really, really complicated interface, or both. Those classes, they just don't give us much leverage against complexity. In fact, in the worst case, the additional overhead of the interface adds more complexity than what you've hidden underneath the interface. It's a net negative. What we'd like to have, of course, on the other side, is a deep class. Very simple interface with a very large amount of functionality underneath it. I mean, that's another way of thinking about abstraction. Right? The idea of abstraction is we're trying to provide a simple way of thinking about something that's actually quite complicated underneath. So deep classes are good abstractions. And this notion, you can apply it to classes, you can apply it to methods within classes, you can apply it to interfaces in general, or modules in a system, or subsystems, anything like that that has an interface or an implementation. Yeah, question?
Because it seems important to give at least a few hints at the beginning.
This is what I give them before, well, it's concurrent while they're doing the first project. We don't have enough time for me to go through all the ideas before they start designing. So while they're designing, we're talking about this stuff in class. Here's a classical example of a shallow method, which I have to say I see distressingly often. There is essentially no information hiding in this method. In order to use it, you pretty much need to understand the complete implementation. And by the way, there's almost no implementation there. In fact, this is so bad that it takes more keystrokes to invoke the method than if you just did the body of the function yourself. So it's basically a complete loss, just adding complexity and getting nothing back for you. Another example of a relatively shallow class I see all the time is a class for list manipulation. This is very shallow. I mean, lists are really easy to manipulate. It's 2 pointers. We know the pointers are hiding underneath there someplace anyhow. And so that's a very shallow class. Now, you can't always eliminate shallow classes. Sometimes you end up, the best you can do is a shallow class. And so I wouldn't say you should never, ever have them. But a shallow class doesn't buy you much from a design standpoint. It doesn't help you in the fight against complexity.
So I think one thing that is perhaps a bit subtle is that the size of the class is not the amount of code that is in it right now. It might be the amount of code that you eventually have to add, or if you have to have multiple implementations of it, right? So maybe this doesn't make sense in isolation, but perhaps there is something else which is, there's another implementation of it maybe right now or in the future, which is going and storing stuff in a database or something like that. And so I kind of wonder if you disagree with that characterization that you need to keep track of the evolution of the class in mind when deciding on its depth.
Well, I agree with that. In fact, the whole idea behind software design is we're doing things for the future. We're doing things today to make it easier for us to develop in the future. And so you have to think a little bit ahead. Although, of course, the classic problem with software is we can't visualize the future very well, so it's dangerous to try and think too far ahead. But I agree with your concept in general. In this particular case, though, the problem is that the interface is already so specialized that there's just probably not a lot of room for wiggle room under there. Almost certainly anything you change to the implementation is probably also going to change the interface. And so, again, it's probably not going to help you. But if you have reason to believe it will, well, yeah, sure. So the problem that leads to this, and by the way, I think this is one of the biggest mistakes people make. Too many, too small, too shallow classes. And the reason people do that is because they've been taught classes and methods should be small. How many of you at some time in some course were taught your method should be small? And how many of you have been given a number? Like any method larger than n lines, you should chop it up. How many of you have heard something like that said? Okay, tell me a small value of n you've heard. What, 20? Has anybody heard 10? I've heard 10 sometimes. So if you take this to the extreme, this results in what I call classitis. Classitis is when somebody says classes are good, and somebody else thought what they heard was more classes are better. And so under classitis, your goal is to have as many small
Have you
classes
heard
as possible,
5?
where each class adds the tiniest possible amount of new functionality to the previous classes. If you want more functionality than that, make another class.
Wait, who in the world says if you've got more than 5 lines of code in a method, you've got to break it out into 2 methods? That's pretty good.
Probably the best example of this in the world today is the Java class library. There's nothing in the Java language that requires this, but somehow this has just become the culture in the Java world, these tons of little, tiny, shallow interfaces. Like, for example, the thing that just bugged me about Java when I started programming, if I want to open a file and read serialized objects from it, I have to create 3 objects for that. First, I have to create this file stream, but for some reason, I don't get buffering. If I want buffering, it's like, do you want to eat today? So on buffering, I have to create another object. And then if I want to read serialized objects, yet another object on top of that. And each of these control exceptions that I have to catch, and then exceptions can come halfway through, and I have to do cleanup. An enormous amount of complexity for something that's really, really simple. So I think they lost sight of the idea that, first of all, in managing complexity, the common case matters a lot. You want to make the common case really, really simple. I shouldn't have to do all of this. Okay, maybe I want to be able to not have buffering, but that should be an option that, if I don't want buffering, that should be where things get more complicated. Not I have to remember to ask specially for buffering. So to me, it's not about length. Length is really not the fundamental issues. I don't have problems with methods that are hundreds of lines long if they're relatively clean, and if they have a deep interface to them. It's abstraction. That's the most important thing. So rather than striving for length, you should first try and get these deep abstractions. And then if you end up with something that's really big and long, then see if you can chop it up. But depth is more important. So what's an example of a deep interface? My favorite in the world, probably one of the most beautiful interfaces ever invented, is the Unix file I/O interface. 5 functions. Falling over easy interfaces to every function. The only complexity is the flags and the permissions for opener, a little bit funky, but everything else is very, very simple. And then think about what's hidden behind this simple interface. There's typically hundreds of thousands of lines of code behind that. They do everything from managing disk space to file caching to device drivers, enormous amounts of code, and of course many other lower level interfaces behind this. But just this amazingly beautiful 5 functions. Now today people look at this and think, well duh, of course, that's the way you design things. But it was not like this. Anybody in this room actually programmed at around the time Unix came out? And only a few of us are old enough to have done that. Things were pretty horrible before then. Like, for example, in pre-Unix file systems, there would be a totally different set of kernel calls if you wanted to open a file for random access versus sequential access. 2 different sets of kernel calls, different kinds of files. You have to declare your file, random access or sequential. And Unix just had this amazingly simple interface. So yeah, a beautiful example. OK, let me go to my second design principle, which is define errors out of existence. So we all know that exceptions are a huge source of complexity in systems. For example, in the RAM cloud storage system, we thought we were building a low latency storage system and figured out we'd be spending all of our time making things really fast and low latency, but in fact, 90% of our time went into doing crash recovery. So they're a huge source of complexity, and again, the common wisdom kind of leads people astray. You're taught to program defensively, which is good, but people then think, I should be throwing lots of exceptions. The more exceptions I'm throwing, the better defense I'm doing. And as long as I, building my module, catch all the errors and heave them up in the air as exceptions, I don't have to worry about where they land or who's going to deal with them. I've done my job. In fact, the more of them I throw, the better a programmer I am. But then that just results in this explosion of exceptions that have to be caught and handled, and then the exceptions themselves create more bugs, and you have secondary exceptions and so on. So I would argue, in general, overall, we should try to minimize the number of places where you have to handle exceptions. You can't completely eliminate it, but try to minimize that. And the best case of all, which I found you can do surprisingly often, is simply to redefine the semantics so that there is no error. There is no exception at all. That's the best. It's just gone completely. So let me give you 3 examples of that. First one, when I was designing the Tickle scripting language many years ago, I introduced an unset command, which deletes one or more variables. When I was doing this, I thought, by the way, this is a classic mistake people, I thought, why in their right mind would anybody ever delete a variable that doesn't exist? That makes no sense. So I'm going to throw an exception for that. Well, it turns out people do that all the time. For example, you're halfway through a computation, you decide you just want to bail. So you want to clean up all the mess you might have made. So you go through and delete every variable that you might have created, but you don't know which ones you actually got around to creating yet. And so some of them don't exist. So in practice, people complain about this all the time. And in fact, if you look at Tickle code, I bet virtually every invocation of the unset command is wrapped in a catch command that will catch the exception and throw it away. That happens.
You're right. You're right. Methods can be no longer than 5 lines of code. What? How do you even? There you go. Somebody wrote it down and published a blog article about it. Well, maybe there's a case.
So what I should have
don't know.
done,
That seems like a lot.
I don't know why I didn't fix it once I found the problem. That was my second mistake. What I should have done was redefine the semantics so that unset makes a variable not exist. And if you think of it that way, well, if the variable doesn't exist already, we're done, clean, no harm, no foul. And so that's what I should have done. Should not have thrown that exception. Another example is file deletion. In Windows, at least in the early days, if you tried to delete a file when some process had the file open, that was not allowed. Anybody experience this? Anybody use Windows experience this? It's this horrible thing, and then now you figure, okay, who's got it open? You start going around killing programs to try and make it to delete the file, and you can't find which program has it open, so finally you just give it and you reboot. And then it turns out, that it's a system daemon that has the file open, so when you reboot, it's still in use. You can't delete it. So Unix has a beautiful, really lovely solution that makes this error go away. In Unix, if you delete a file while it's open, what happens is it deletes the file from the directory and from the namespace. It no longer appears anywhere in the file system. But the actual contents of the file still hang around so that any process that's using the file can continue to access the file. And then when the last open instance of the file is closed, then finally it cleans up and throws away everything else. It's a lovely solution, because you could have made the other mistake, which is say, I'm going to delete the file, and now anybody doing I/O on the file gets an error. That would probably be even worse, because now every program would have to be written to handle the case where the file goes away in the middle of your accessing it. So Unix had this beautiful solution where there's no errors on either side. It just does the right thing. So at Windows, they eventually realized this was a problem. And I don't know where they are in the evolution of fixing it, but I know that the first stage they did is they had some special flag you could set would say delete the file even if it's open. Or you could, maybe when you open the file, you could allow it to be deleted while it's open. But they didn't get rid of the directory entry. They kept the directory entry around. And so you couldn't recreate the file while it was open. So if you were, for example, trying to rebuild and the binary was in use, you couldn't modify couldn't create a new version of the binary file because the directory entry was locked down. So they still didn't get it right. So again, examples of why you just want to make these errors go away. A third example, which is people often consider more controversial when I say this one, is substrings. So in Java, there's various methods that will extract a substring out of a string. And these methods are very exception happy. If either of the indices is outside the range of the substring, it throws an exception. And I believe if they're kind of out of order, it throws an exception. I find this a huge pain. I end up typically having to write my own code to effectively clip my indices to the range of the string before I invoke the Java substring command, so I won't get these exceptions. Again, I consider this just a bad idea. Instead, it would be so much simpler. Just define substring so that it returns the overlap between the indices you've specified and the available contents of the string. So if both of the indices are outside the range of the string, it returns an empty string. If they're in reverse order, clearly there can't be anything in the right order. It doesn't return. And it just does the clipping automatically. This would eliminate so much extra code people have to write, and also, I suspect, a lot of runtime exceptions that occur because people forgot to clip their indices to the range of the string before they invoke the command. So again, the overall idea here is to try and reduce the number of places where people have to deal with exceptions. The book talks about a few other ways of doing this, but the best...
Right, so his point there is, in the code that you're writing, just handle the edge cases. Don't throw exceptions. Just make sure that the edge cases are handled. And so that's like that's his point. Define errors out of existence means write the extra code so future developers don't have problems.
The best case of all is just to define the exceptions away. Just make the normal behavior always do the right thing. And nobody's objecting on the Java subject. Usually somebody raises their hand and objects to that.
Yeah, so not objecting, but define intuitive semantics perhaps is a more complete definition. I mean, you could simply say, okay, whatever set of parameters you pass, you have random behavior that are difficult to explain. But the examples you gave were very, very intuitive, like when you define the overlap between the indexes and the available space, or the TCL, etc.
Somebody want to argue that Java substring should throw exceptions? Let's bring the microphone up here. I know some of you are thinking it, so yeah.
I think it should throw runtime exception because like you can sometimes it could be just the wrong assumptions on client side, like they just done something wrong and they're assuming that's correct range, but it's not. I think it should be runtime exception.
This is part of the philosophy about we're going to try and keep people from making mistakes. So which it's a kind of a noble thought, but the problem is that it's really hard to keep people from making mistakes. And so typically what happens when we try and do this is we introduce lots of complexity, which makes it hard to even do the right thing. And so I'd argue in general we want to make it really, really easy to do the common case and the right thing. We should have, you still have to do testing to catch mistakes. And so this isn't going to replace the need for unit tests. But in general, I think when you try and build systems that can keep people from making mistakes, you usually create a whole lot of complexity for everybody.
So how do you distinguish between Java substring versus Java.string.character at index? Should that throw an exception if the index is out of range?
Good question. That one probably should, because you can't really return a character. What do you, if you could redefine a kind of like IEEE floating point did, where there were special values that represented arithmetic errors and things like that. So if you had some sort of a null character that you could return, that might make sense. But we don't really have that in our character sets. So in that case, you really can't. I'm not sure what you would return if you're going to return something. So yeah, so in that case, you probably do have to throw an exception.
Question. So one question. So when is it a good idea to actually throw exceptions? So there are intuitive cases you want to eliminate exceptions as much as possible. Then how do you decide, no, there's nothing that I can do, my changing semantics doesn't work, and I really have to throw an exception now?
Well, if you fundamentally can't carry out your contract with your caller, if you can't implement your interface, then you sort of have to throw an exception. Like if you're reading, for example, doing a read operation and the read can't succeed because you got an IO error, you have to, that's information that you do have to reflect that back to the caller. So you can't eliminate all exceptions. Some of the students in the class thought this was really a great idea, and so they basically wrote no exception handlers in their code. I said, I'm just defining them out of existence. I said, no, some of them actually matter. You have to, and a lot of software design, I think, is figuring out what matters and what doesn't matter. And ideally, you'd like to make as little matter as possible. You'd like to be to not depend on very many things, but you have to recognize the things that really are important and do matter, and those you do have to reflect in the system.
Yeah. Do you have thoughts on exceptions versus extra status code or extra error code returning?
Boy, that's a classic argument. Exceptions versus return values. There are times when each makes sense. I believe exceptions actually provide the most value when you throw them farthest. If they're going a long way up the stack, that's where they provide the biggest benefit, because you've made it unnecessary for a whole bunch of intermediate layers to deal with the situation. You can take it all the way back to the source and deal with it at the source. If you are catching exceptions in methods you call, there's not as much value for that compared to just getting a return value. It's not a whole lot different. And one of the problems with exceptions is also they all have clunky syntax. And actually, checking a return value is actually simpler syntactically than declaring an exception handler. But a lot of times, some of these exceptions, you really will want them to propagate a long ways. And so then, even if the caller is going to look at it, you probably want to manifest it as an exception rather than return value.
Any thoughts on crashing as a way of avoiding passing along?
Any thoughts on crashing as a way?
Yes.
Yeah. Actually, crashing is a fine thing to do in certain situations. Like, for example, in most programs, I would argue you should not be trying to count out-of-memory exceptions. It's just hopelessly complicated to try and do that because you depend so much on memory that for most applications, if you run out of memory, just crash. Print a message and crash. It almost never happens. Machines today have tons of memory anyhow. I think, again,
just want to be clear that maybe he never has a memory exception, but I can tell you, I've written some memory leaks. I know what's going on.
With caution, but I think there are situations where just crashing is a fine way to do it. The alternative would create so much complexity that you probably wouldn't get it right in the first place, and you'd end up crashing anyway.
Hey John, there's 17 questions on the Dory, so I'll just ask the top ranked one so that we don't run out of time. The question is from Kun, and in real life, development is often under various constraints. For example, tight schedule, need to experiment and be flexible about design, lack of mature tools, library, etc. Does your approach to software design philosophy change based on real-world constraints?
Yes, and actually, that's a good lead-in. Let me move on to the next part of the talk, which I'm going to talk about that. And I think I want to keep moving, too, because we're starting to run a little tight on time. Think about a couple of specific techniques or philosophies you can use, but I think one of the biggest obstacles to good design is mindset. If you don't have the right mindset, you will just never produce a good design. And I think there's two ways of approaching the programming or design process, which I call tactical and strategic. Unfortunately, most people take the wrong approach, which is the tactical approach. In the tactical approach, your goal is to get something working. You know, your next feature, fixing a bug, whatever. But that's your goal, to get something working. You think, how can that be wrong? Isn't that the whole goal of building systems? We want them to be working. Well, the problem with this approach is that when you do it, then you usually have the mindset that, well, I'll try and make it mostly clean, but if I take a couple of shortcuts or a little bit of kludges, as long as I don't do too many of them, if I get it working, that's what really counts. The problem with that is that those kludges build up really fast, because not only are you doing it, but everybody else on your team is doing it. And then after a while, you start saying, probably shouldn't have made that decision back there, but we've got our next deadline we've got to hit. I'll try and find time after that deadline. But then by the time the deadline's done, you've introduced so many kludges, you realize it's going to take weeks to fix all these, and you don't have time for that. And so it just never happens. So the result of this, inevitably, is the system turns to spaghetti really, really fast. And the problem is that complexity isn't one mistake you make. It's not a single big thing that makes a system complicated. It's hundreds or thousands of mistakes made by many people over a period of time. And so that means, first of all, you don't notice it as it's happening, because it's just a bit at a time. But then even worse, once it's happened, it's almost impossible to fix, because there's no one thing you can go back and fix to fix the problem. It's thousands of things in hundreds of places. And so it's just so overwhelming you never get to it. So by the way, there's an extreme of the tactical programming, sort of personality type, I call the tactical tornado. This is a person who turns out enormous amounts of pretty shoddy code that kind of 80% works at a huge rate and leaves a wake of destruction behind them. And in many organizations, these people are considered heroes. This is who management goes to when we need the new feature for tomorrow. And they'll have a feature tomorrow that works for most of the day tomorrow, anyhow. In fact, actually, when I gave this talk, somebody said, oh, is that what you mean by the 10x programmers? No. How many of you feel like you've been in the presence of one or more tactical tornadoes over your career? Yeah, every organization has them. I'm sure they're here at Google. And unfortunately, one of the things I hope to do is to provide a name for this so we can start calling them out and maybe educate management about them. How many of you feel like your management actually rewards tactical tornadoes? Yeah, that's even worse, unfortunately. So, the tactical approach is really, really easy to slide into. Very hard not to do that. So the first thing you have to realize, if you want to do great design, you have to realize working code is not enough. That can't be the only goal. It's table stakes, of course, things have to work, but that shouldn't be the real goal. Instead, you should take what I call a strategic approach, where the goal is a great design. That's the most important thing. Yes, it's got to work today, but we have to have a great design. Why do we want a great design? It's so that we can develop fast in the future. So it's really all about investing. We'll invest in good design today, because most of the code we develop is going to be in the future. And so if we mess things up today, we're slowing ourselves down for the future. See?
You know what's really interesting about this one, where he's talking about investing in the future, coding for the long term, it's such a different mindset when you're working in the product field versus when you're working in the agency world, right? Like, it's just, in agency, you're like, get it done, get it finished, get it out the door, deliver the code to the client, and then see ya, and like, you just let them go with it. But in product, like, the mindset that he's right about this mindset, the mindset you need for that. And I recall trying to do this at agency, but even like, if there's a large refactor that you want to do and that you need to accomplish, like ongoing stuff, and you just, who's going to pay for it? Nobody pays for the work you need to make these investments. And so moving to product is a great way to get better at long-term architecture.
You have to think about complexity, try and find ways to drive complexity out of the system. And fundamentally, and this is the hard part, you have to sweat the small stuff. You sort of have to have a zero-tolerance approach. Don't let those little bits of lint creep in, because if they do, then you're going to slide back into a tactical mode again. So if you program strategically, you're going to go slower at first, but presumably, in the end, you'll end up going faster. I mean, even with the strategic approach, your development will still slow down over time, because complexity is inevitable. We can't prevent it. We can only kind of slow the growth as much as we can. But eventually, you'll end up programming faster. So the issue is you have to invest. If you're not willing to take a little bit of extra time today, at least a little bit, you can't do good design. But in my opinion, it all pays back. You always get your investment back. Now the challenge is, what are the parameters of these curves? Like, how much slower do I have to go initially? When do I get to the point where the slopes are the same, so I'm at least now running as fast as I was tactically? When do I actually catch up, so I'd actually have a net gain? And then how much faster do I go at the end? And this, unfortunately, I don't know of any quantitative answers to any of those questions. I have opinions. Like, my opinion is that the crossover period is somewhere in the 6 to 12-month range, roughly how long it takes you to forget about why you wrote that last chunk of code. But I don't have any data to back that up, unfortunately. So that's the challenge, because people can see the cost today, but they can't really estimate when the benefit's going to come or how long in the future it's going to be. And so it's really easy just to optimize for this part down here.
Yeah, just a quick question. Have you thought of analyzing open source development and seeing whether or not you can observe this? I mean, it would require some judgment calls, I guess.
I'm not sure how you do. You can look at the rate of commits or the new lines added, but the problem is you don't know how much effort went into those.
Yeah.
So
I was thinking, like, when a new storage device comes out and people will write new file systems or something, you could look at this across different OSs and see how things happen. But
that's a thought. It's hard. So the question is, how much do you invest? Actually, let me charge forward for a couple more slides because we're starting to run a little tight on time. So what's the right amount to invest? And if you look at most startups, honestly, they're mostly completely 100% tactical. They feel there's tremendous pressure to get the products out. Our financing is going to run out
Absolutely
in 6 months.
true.
Whatever evil we put in with our, when we become famous and wealthy and do our IPO, we'll be able to hire more engineers to clean up this mess. And so, they end up with these horrible spaghetti code bases. And unfortunately, of course, once you get that, it's pretty much impossible to clean up. I've never heard of anybody. Maybe if you could go back and completely rewrite, you could do it. Maybe there have been examples of that, but almost never happens. So to me, Facebook is the poster child for this. They even built it into their company motto: move quickly and break things. And they did both of those. So now, in a sense, developers kind of like this. If fresh college hires could come in, they're super empowered. They push their first commits, and they're changing the website in 1 week. The first week on the job feels like really empowering for them. But their code base was just a notorious mess. One summer, a couple of my graduate students went there for internships. They came back and they just couldn't believe what they'd seen. And this was interesting because my students had been whining for the whole previous year about, why do we have to write unit tests and write documentation? Linux doesn't have any unit tests, and Linux doesn't have any comments. Why do we have to do this? I never heard that again after they came back from Facebook. So Facebook has eventually realized this, and so they changed their motto to move quickly with solid infrastructure. It's like, no, I meant to say wouldn't, not would. So have they been able to fix it? I don't know. Now, people hear this, they say, well, yeah, but Mark Zuckerberg is the 4th wealthiest person on the planet. How can this be a bad approach? And of course, the answer is you can be successful with crappy code. You can be tactical and build companies that succeed. Facebook has done it. But I have 2 thoughts on this. One is you can also succeed with the other approach. And although I don't have personal experience with either of these companies, my sense is that both Google and VMware took a much more stronger design culture approach, at least particularly in the early years, 2000 to 2010. Those were the 2 companies known in Silicon Valley. This is where the really great software developers go. They really care about design, and they do really good coding. And the reason this matters is that if you have that culture, I think you're in a much better position to recruit the best programmers. And we know about this 10x phenomenon. The best way to get great products out fast is to get the best programmers. And so I think the strongest argument in favor of a good design culture is that it allows you to hire top people, and that will give you an advantage. So you can do things the crappy way if you want, but there's enough success stories to show that you can make this work. You can do the investment approach. But then again, but how much to invest? I would say, how much can you afford? Just ask yourself, what's the most we can afford at this stage in our lifetime to invest? I think in terms of maybe 10 or 20%, something like that. I bet almost everybody, you can afford to go 10% slower today, realizing you're going to get it all back. It's not a sunk cost. It's all coming back to you in somewhere, 6 months to a few years, you're going to get it all back again. You can afford to do that. And I think in terms of small steps, not heroics. You can't spend 6 months and completely design the whole system from first principles before you write any code. That doesn't work. We know one of the problems with software is we can't visualize the way our systems are going to turn out. You have to use a somewhat iterative approach. So I'd say think of it in terms of small steps. So when you're building new modules, take a little bit of time to design the interface, try to come up with deep classes. Write the documentation as you're going, unit tests, of course. And then whenever you make changes, you have to realize you can't get it right the first time. It's one of the rules of software. We just can't. So assume every time you're in a system, you're going to have to be improving things. Always look for something you can make better. And one reason for this is you're probably making something worse when you go in also. So even if you just want to break even, you got to find something to improve. So just think of it, I'm just trying to at least break even. So and this is against the normal philosophy. I think oftentimes when people are changing existing code, they go for what's the smallest number of lines of code I can possibly change to do this. I think sometimes it's because they're afraid, I don't understand this, I'm going to break something, so I'll make the fewest lines of change, so I'll just kind of directly access a global variable in another file rather than trying to find a clean interface for it. So don't do that. Try and find a clean way of doing things. And ideally, in the best case, you'd like to end up where you would have ended up if you had built the whole system from scratch, knowing what you know today. That's what you like. Is this the way we would have done it if we'd built it from scratch? That's the ideal. Now, you can't always do that. Sometimes that would be a refactoring that's way beyond the scale of what you can do. So again, I would just say, ask yourself at any given point in time, am I doing the most I possibly can? Don't just give in and say, hey, the boss says we've got to get a release out tomorrow, so I'm just going to hack this thing in and make the boss happy. Ask, is this the best I can possibly do?
John, you didn't touch on layering, which is often considered very good in software engineering, but it also has a challenge of performance of the code when it executes. Often the functionalities are replicated in multiple layers, and it's not clear how to distill that without mucking up the code.
So which is your question, are layers good?
Yeah, so how do you deal with layers, the demand for abstraction in layers and the demand for performance, both contradicting each other?
We need layers for managing complexity, so in that sense they're good. They do have problems for performance. I think people do too many layers. I think that's a common mistake, is to throw in lots of skinny layers, again, rather than having a smaller number of meteor layers. That's one problem. The other thing is that for cases where performance matters, if you think a little bit about what your key performance metrics are, I believe you can often define your layers in a way that allows you to achieve very high performance, even with layering. But you have to be thinking a little bit about so at least the overall kind of gross level performance metrics while you're doing your system design. Okay, so anyhow, I think this investment thing is the biggest challenge, particularly because a lot of managers, I think, don't really get it, and they're sort of pushing for the next feature or the next release. And I don't know how to combat that except to have the people that everybody recognizes as the great engineers in the company go to management and try and get management buy-in. And I think it'd be great if companies could have sort of explicit, this is in our engineering philosophy, we will invest at sort of 10%, we assume, roughly on average, 10% of our resources are going towards making designs better, not just cranking out next features. Yeah, John.
Fun story about Zensurance, actually, is we do 2-week sprints, and we have a 30 to 40% tech debt budget, which is effectively just about that every 2 weeks out of all of the products, all of the parts of the code, so we work on 60% new features and 40% cleaning up the old code base. So it is, there are places out there like Zensurance where we do feel like investing in the long-term quality of the code is the best way to go. Anyways, that's so.
Hi, John. I haven't looked at this for 20 years now, but the quantitative analyses that you're describing were the domain of the software engineering community for a while. I'm wondering if you sort of poked into that space to see if they have experimentation, numbers, analyses that might be useful, or have they just dropped off the map?
I haven't looked very carefully, partly because I'm sort of skeptical that it is possible to measure it in a meaningful way. So I haven't, but I would love to see numbers if they were believable, but I haven't looked enough to know. Okay, so I just have a couple more slides and open it up for questions. So is the course working? It's hard to tell for sure. I mean, you can't become a great programmer in 1 quarter. It'll take still lots of experience for these people. We'll have to come back and ask them once they've been out in industry a while. This is just the sort of the first step in the process, I think. But the class has a really fun energy to it, really fun. The students start off in the first round of code reviews, and they're very tentative, kind of afraid to criticize each other and not really sure what they should be saying. So the first round's kind of tentative. Then they meet with me, and they get unloaded on. And then they start, oh, okay, I can do that too. And so about halfway through the second code review, typically the tone of discussions changes, where students are now being more critical of each other. We have these interesting arguments in class about whether one approach is more complicated than another. And it's really clear by the end of the quarter that the students are thinking about programming in a very different way than they thought about it before. So I think that's really encouraging. I will have to say, though, even if the students don't become better designers, actually, I'm becoming a better designer from teaching the class. It's really interesting for me. You might think it's tedious reading 20,000 lines of code in a week 3 times over a quarter. And it does take some time, but actually I learn a lot from that because the students are all doing the same thing in the same language, and so I can see different approaches, and I can see common mistakes that they make. And actually what's ended up happening is I've changed my view about a couple of design issues as a result of teaching the course. And in particular, the one at the bottom of the slide was I realized that making classes just slightly general purpose, even though you're only going to use them in one place, actually makes them amazingly simpler and deeper. I hadn't realized that until I saw some student project section the second time I was teaching the course. So it's been really interesting for me to see this, and I feel like I'm learning more about the process of software design and getting better ideas for how to teach it as I go. And as I've talked to people about the course, people kept saying, well, you should write a book on this. And I was on sabbatical last year, so I decided, okay, I would do that. So I have written this book. It's a relatively small book, 170 pages. Again, still fairly philosophical in nature, more than prescriptive. So the hope is that I can reach more people, because I can only teach 20 people a year in the class. I can't do more than that. And ideally, I'm hoping the book will kind of be a lightning rod that maybe we can kickstart a discussion. I hope people write to me and disagree with things in the book, or suggest other design ideas, or provide better examples. I'm also trying to define terms that people can use. One of the things I hope maybe the book can do is people can use that in design reviews, to have ideas and ways of talking about design in design reviews. Actually, I have a question for you. How many people here do design reviews? I assume almost everybody. And how many of you in your design reviews, it's common for you to discuss design issues as opposed to coding style and bugs? How many of you commonly talk about design things? Good, great. I'd like to see more of that. So anyhow, the book's been out for a couple of months. If you read it and have thoughts or comments, I'd love to get your input on it. My view is this is just a first stab. If this actually ends up being a useful book, it'll probably be, it's kind of like software, about version 3, where it really hits its stride. I'll need to get feedback and revise and fix things that are wrong and add new ideas. So just to conclude, I really believe we can teach software design. I really believe we can. My current approach, unfortunately, is woefully non-scalable. I haven't figured that out. I really need somebody with a lot of experience, I think, reading the student's code. I feel like some principles are emerging. If you read the book and agree or disagree with me, I'd be curious to hear your take on that. What I hope to do in the future is just to...
I should take a second. One of the other links that I have, I wasn't expecting to do this whole video today, but it's may as well call this the whole thing. And we'll read Gergely's review of it, but my understanding is that some of the, it's a short book, and some of the chapters are only like 3 or 4 pages at a time, so it's easy to pick up and get through, is my understanding. So
somehow leverage this out into the community. I'd love to see just a greater sense of design awareness in the software community as a whole. Can we have the discussion? Can we make that an important part of our community? It's just so sad that we don't really even have the discussion today. So I created a mailing list for discussion topics about the book. Hasn't been much traffic on it so far, but I hope there will be more in the future. And again, I hope to take ideas from people and make the book better and better and the class better over time. And the long-term goal is, it'd be great if 5 or 10 years from now, we actually have a relatively robust set of principles that most developers agree are good for software design. So thanks for your attention, and I'd be happy to take more questions.
So let me get a few questions from the Dory out here. Do testing considerations like unit testing or mocks influence interfaces and abstractions?
Testing considerations. I'm a huge fan of particularly unit tests. Crucially important. I've debated whether to try and teach them in the class. Actually, I did a little bit in it one time in the class, but it was too much of a distraction for the class. We only have 10 weeks, and so I finally decided for the class, I just got to focus on design. So I don't do unit testing in the class, but I'm a complete advocate of unit tests. I can't imagine doing software without unit tests.
So I was intrigued by your, in the first part of the discussion, when you said in the iterative process, you actually dropped, you initially had students build on other students' code. To me, that's a very, very real world problem, and I'm just surprised that I wish you would teach that.
I agree with you. In a perfect world, that would be one of the things we do. The problem is we've got 10 weeks. How do I use that 10 weeks? And I decided I want to try and do the most I can on design. And so I have to sacrifice other things. That's the same reason why unit testing got thrown out, because I felt like it was better for them to be thinking about more design issues than unit testing issues. But I agree with your thought completely.
Do you have TAs for the course?
Do we have TAs? Yeah, me. Not right now, because I'm just worried that the TAs would not be able to give high enough level of feedback. I've started wondering if maybe students who have taken the course previously could TA. So far, actually, the demand has not been more than my capacity, and so I've been able to keep it small. If the demand grows, I may try and experiment to see if previous course participants can TA. But again, I worry. And also, for the first few offerings, I wanted to read all the code myself, too, because I wanted to learn from it as well. So.
Have you thought about using software engineers as TAs? We read and write code every day.
I'm not opposed to it in principle, but I want to make sure students don't get mixed messages. And so, particularly because the ideas I'm teaching in the course are not ideas that are not necessarily widely spread in the community. Like the worst thing would happen is if a software engineer comes in and says, no, this method is longer than 20 lines, you've got to break it up. That would be so if I could find people that are sort of bought into the philosophy, and maybe if the book gets out there and more people, maybe we could do more of that.
Okay, one question from the Dory, the second highest rated one. Are threads still a bad idea?
One of the interesting things when the only form in which you publish something is a set of slides rather than a paper, which that was just an invited talk at a Usenix conference a long time ago. It's interesting. People can come back and interpret that in whole bunches of different ways over the years. So that was done in a very narrow context of the time, where people were starting to introduce threads for things that didn't even need threads. They were doing threading on machines that didn't even have multiple processors on them. And so that talk was a reaction to that. Threads are unavoidable. For certain things, you just have to use them. But they're still they're sort of the next to worst alternative, where the worst alternative maybe in some cases is not using threads. They're incredibly hard to program. So I'm still not a fan of threads, but they're kind of a fact of life.
I have a question on the Tickle language. I think the language is sort of very simple in itself, but eventually not gain like larger scope of adoption. I want to ask, because you are the language inventor, like, is there like high-level issues in the language design you think you got it wrong, which makes it?
Whatever happened to Tickle, I think would be your question. I don't want to diverge too much on that. I would say two things. First, one of the things Tickle was best at was doing kind of simple interactive GUIs with TK. And when the web came along, the web basically took that over, and Tickle did not make the transition to the web. So a lot of things people would have used Tickle TK for, they ended up doing in the web. Second thing is it really the right language? I'm not sure in retrospect that it's the right language. I built it for a very different purpose. I built it as more of a textual command language. You'd be typing commands to programs, almost like a shell language. And then it ended up getting used as a scripting language. It has a bunch of interesting properties, but I don't know, if I were doing it again, I'm not sure I would design the same language. But I think the biggest thing that happened is the web came along, and Tickle did not effectively make the transition to the web.
Okay, so there's a lot of really interesting questions both on the Dory and in the room. In the interest of time, I'm going to do 2 more Dory questions and 2 more in the room. And then John is going to stay around and hopefully answer more questions as well. Okay, so any thoughts on the hiring process based on what you've observed? And the question has, how would you change the hiring process, which is so algorithm heavy? Can you share your experience when you ran your company?
Hiring process, actually, I'm not sure it relates to software design, but I have a very strong opinion about hiring process, which is you should hire for slope, not y-intercept. I think people, when they hire, they do a pattern match of what this person has done, try and find the person who has exactly done the job we want to do. I think that's the wrong way to hire in general. I think you want to hire the person who's the fastest learner, who has the fastest slope. I don't particularly care whether they've done the job I want to do, because particularly in a startup when things change so rapidly, things change. So I look for people who are really smart, fast learners. Also, by the way, the person who's done this job 5 times before, you sort of wonder, well, why haven't they moved on to the next job? Oftentimes, those people have kind of hit their plateau, whereas the person with the rapid slope has the potential.
Okay. Last question from the Dory. What do you think about Hiram's law?
Sorry, remind me what Hiram's law is?
It says, I Googled it, and it says, with a sufficient number of users of an API, it does not matter what you promise in the contract. All observable behaviors of your system will be depended on by somebody.
I think there's truth to that. Yeah, over time, what happens is the sort of application, they find every crevice and sink their roots under that, and they will discover. So unless you're very careful with your APIs, I think that's probably true. Sad, but true.
Hi. Have you observed any change in the simplicity or the complexity of a software design based on the choice of languages and supporting ecosystem?
Oh, a good question. Are there some languages somehow lend themselves to better design than other languages? There probably are. I think that's mostly a secondary, sort of second-order thing. But for example, today I'd rather program in C++ than C, because I like some of the object-oriented features in C++. Now, C++ is sort of a big beast of a language with a horrible learning curve, but I appreciate the power of it. But honestly, I think the design principles are fairly universal. You can use them in any language. That simple file system interface for Unix was done in C with no object-oriented stuff. And then people that say, oh, no, actually, you notice it's actually object-oriented because there's a file descriptor that gets passed around, and the object-oriented was really crucial to that. I say, no, they just found a really sweet interface. So I haven't found one language that somehow is dramatically better than others for design. But if people have opinions, I'd be curious to hear their opinions about that.
So back to hiring, you mentioned we should hire on slope, not on y-intercept, and I radically agree. How do I estimate
How do you measure that?
Right, especially
no
like
idea.
you need at least 2 points, right? In an interview, I get only 1, and I'm terrified of hiring more tactical tornadoes.
I don't know. So I'll tell you what correlated best for me, but it's sort of crazy. Is that I found, in my experience, people worked out best were the ones where I just really enjoyed my conversation with them during the interview. And that's sort of weird. I feel kind of funny saying that, because that means somehow somebody sucked up to me and I liked them and hired them. I don't think that's it, because I have a pretty sensitive meter for suck-upness, and that really pisses me off. And people have also pointed out, but if you take that edge, that's kind of a risk. That you're just hiring more people like yourself, and so you're not going to do diversity very well. So I have no idea what to make of that, or whether it's even a good idea. But that's the one thing that seemed to correlate in my experience.
Okay, yeah. So let's thank John once again now.
There we go. So I actually didn't finish all the way through that, but that was pretty good. And here's one other is I don't know if y'all remember Gergely. I don't remember if we did stuff with him in the first couple of weeks or the first couple of lessons, but he was, it was really good, right, Pabs? It was like, I saw this and I thought, well, shit, I'm gonna buy this book now because it's and actually on Amazon it's only like $9.99. One sec, Amazon.ca. It is not. Oh, philosophy of software design. Yeah, the Kindle edition is on. Actually, the paperback's only $20, but I guess you already have a copy, but like that's not expensive. That's and his stuff was really good. It was a really good talk. But here we go. So here's a review from someone that's a 5-minute review, bringing us to 8:45, and there's really no point in going through. All of these other ones you can do on your own if you're super into them. And I wish... It's too bad because I had found one other course on design patterns that I thought was worthwhile, but anyways, here we go.
Hey, this is Gergely. A Philosophy of Software Design? Is this book any good? Let's take a look. In this review, I'll share 3 things I liked about this book, the things I didn't, and I'll give you my verdict. As a software engineer, should you get this book and read it? The first impression of this book that is short and pretty light. If you look at the chapters themselves, they're also short. Just take a look at Chapter 5, Information Hiding and Leakage. Yep, that was a whole chapter. At first, this shortness made me skeptical. Just how much can you pack into a short book all about architecture? Turns out you actually can if you're a good writer. Talking about authors, who is this author who wrote the book? John Osterhout is a professor at Stanford and teaches a software design class. Students work through a series of projects to practice design principles throughout a semester. John wrote this book after teaching the class 3 times. Now this is really interesting because it's typically not how software design is done. In the real world, you design once and you ship once. You don't get second chances to figure out if choosing a different architecture approach would have worked better. But in John's case, he taught a class with the same amount of people through a semester, then again, and again. And he was able to observe what approaches worked and what did not. And this is how this book was written. This is a very unique approach. I've not seen other books follow this methodology. There are 21 chapters in the book, and you can read each of them in about 10 minutes. The first thing I liked about the book is getting a fresh definition of what software design is. I had my thoughts, but the book came with a new one. The whole idea of the book revolves around complexity. According to the author, software design is a means to fight complexity. Quoting the book, "The greatest limitation in writing software is our ability to understand the systems we are creating. The larger the program, the more people work on it, the more difficult it is to manage complexity. Good development tools can help us deal with complexity, but there's a limit to what tools can do alone. Simpler design allows us to build larger and more powerful systems before complexity becomes overwhelming." The second thing I liked about the book is how it gives a fresh and simple look on architecture. It's not a book filled with complex diagrams. One of the few diagrams in the book is this one. The book is filled with simple ideas and observations, but these ideas compound into something more powerful. In the first half of the book, each chapter introduces an idea on software design and how to manage complexity. So tactical versus strategic programming, modules should be deep, information hiding and leakage, general purpose modules are deeper, different layer, different abstraction, pull complexity downwards, better together or better apart. Each of these chapters talks about a simple approach to reduce complexity. Take the chapter Information Hiding and Information Leakage. This chapter discusses how information hiding and good design are connected. John noticed that students who divided their code into small modules that were shallow ended up with a lot of duplicated business logic caused by information leakage. This also reinforces why John thinks modules should be deep, an idea that I also agree with. The third thing I liked was the chapter on designing twice. This is a chapter that's 3 pages long and caused by information. The thing I liked was the chapter on design it twice. This is a chapter that's 3 pages long.
I just bought the book.
That's
That's why I
simple
was
idea that you should design something twice and then compare the trade-offs. It's brilliant because it actually works. I've seen it in action. And it works brilliant because barely anyone does it. When was the last time that you did 2 different designs? Yeah, I really also do this. To be good at design, do it more and try out different approaches. The second part of the book has chapters on errors, comments, and naming. If you have less experience with software development, you'll probably find this interesting. I didn't get too many new things in the second part of the book. There are two things that I didn't like about the book. First, I really miss how it never talked about how architecture and testability are related. I actually emailed the author who said this was on purpose. Still, I disagree when talking about good architecture, but not talking about designing systems that can be tested by automated tests. Second, there's no ebook and there's no plans for one, so if you want to read this book, you'll have to get the physical copy. So, my verdict? Is it a good book? No. It's a great book. This book is great because it focuses on the essence of software design, a means to reduce complexity. And the book also reduced its own complexity, so it's easy to read. Even the cover is related to this. Up here you see complexity, down here you see simplicity. If you're a software engineer who plans and builds systems, you should absolutely get this book. You can find a link below to buy the book, and you can also read a longer review that I wrote on my blog. If you like this review, subscribe to my channel for more content on software engineering and engineering management. Finally, if you're interested about my thoughts on software design, I've linked an article below on why I think software architecture is overrated and clear and simple design is underrated. Thanks.
Anyway, so that was that. I really enjoyed this one. I did just order a copy, so I'm going to read the full thing. I thought that was good. Anyways, that's the week. Next week is the last week of this series. We'll talk about the behavioral interview, dealing with that portion of it, and for the week of August 10th, going to start going through. So just to prep you, what have we got here? So if I go here, if I go to repositories, did I say this last week? I'll say it again. It doesn't matter. So I've started a new repository to work through. It is to go through Clean Architecture. Clean Architecture is a software design book, much like that one. But I have a copy right over here. Give me 2 seconds. We have So once again, Clean Architecture. If you want to join in on the discussion, chapters 1 and 2. Is this going to autofocus? No. There we go. Chapters 1 and 2, we're looking at 20 pages for week 1. We're going to go through just sort of the intro in an easy way, and then as you see through the schedule, it's sort of chunk out a few chapters at a time and try and get through the whole book to discuss the content. I think my goal will be to be making slides of the content. So your options are to read and come with comments about the content and have your own thoughts on it, or, follow along with the slides and comment on my interpretation or things like that, or, just watch offline at a later date. But there's that, and that's the week. So we will talk to you soon, and thank you so much for coming.